Alright, so this is the 2022 paper for the engineering external, and let's go through it. Alright, so question 1. Stress restoring question. It's asking what is the toughest of the 4 materials. And now if we remember that toughness is the area under the curve, then we should identify that it's obviously not this brittle material, it's not that strong material, it's definitely not that one, it's number 3, C. And plastic question, so wastewater drainage pipe. So there are 2 pipes, water pipes, plastic water pipes that we have to know about, and that's just your general water pipe and your waste drainage water pipe. And you should probably know this from general knowledge that the drainage pipe is going to be polyvinyl chloride, whereas the water pipe is going to be made out of polypropylene. That's just a knowledge question. Drainage, PVC, that's all if you have those pipes coming down from your gutters, leading water away, that's probably going to be PVC. So the answer for that one is D. Question 3. During a race, the rear wheels of a Go Kart exert horizontal force of 100 newtons on the racetrack surface when the gear axle is rotating at 1000 RPM. The diameter of these wheels is 0.28 meters. And we're looking for power. So, let's convert, first because we need to do power, and because we're going to be using this formula, we need T to be in seconds. So let's convert RPM to RPS by doing 1000 divided by 60. And that's going to be 16.67 RPS. And now that we've got that, we can go and say power is W times, force times diameter, distance, on T. So the next thing we need to find is the distance it goes in 1 second. So in 1 second it's going to do 16.67 revolutions, and so we need to find the circumference of the wheel, and the circumference of the wheel is just pi times diameter, so 0.28 pi, which is 0.88 meters. So now that we know that, we're just going to go and say power is force times distance over time, which is 100 times 0.88 times 16.67, the revolutions, divided by 1. And that is 1,467 kilowatts. And that's going to give us C. Alright, question 4. Alright, so we have to use circumference again to find the distance that 1 revolution of this takes by the look of it. So velocity ratio, yep. So this is 5 millimeters, it's going to move in 1 revolution of the handle. That's a red herring there, you don't need to know the pitch. So that's just going to be pi, circumference is going to be pi times diameter, or pi times 2 pi r, which is 2 pi times 0.1. Which is 0.63. The velocity ratio is going to be distance of the effort to distance of the load, likely. I think that's the right order when we're doing ratio. I know it's distance over dl when we're looking for a value, but when it's a ratio, I'm not too sure. But we can just flip it on its side if it's wrong. So that is 0.63 to 5, so we are going to need to flip it. So 5 divided by 0.63 is going to give us 7.9. What have I done? Oh, of course. My bad. I need to remember my units. That's 5 millimeters, so 0.005. 0.63 divided by 0.005 is going to give us 126, and 0.005 divided by 0.005 is going to also give us 1. So the answer for this question is B. Alright, so let's draw a diagram for this one. We've got a water tank 7 meters above the ground, and it's 3 meters tall. So that means the center of gravity of this water tank is going to be at 8.5 meters. But we also have we want to find the potential energy relative to the water outlet, which is a 1 meter above ground level. So we just subtract 1 from all of these, and the value that we'll be using now for the height of the tank is going to be 7.5 meters. So, potential energy is going to be 20,000 times 9.8 times 7.5. And that is going to give us 1.47 megajoules of energy. And that is answer A. Carbon phase diagram. Okay. So, this is just knowing what phases are in each section. So in this section here, first of all, austenite does not exist above the eutectoid temperature, below the eutectoid temperature. So this is only going to be ferrite and cementite on the lower side of the eutectoid temperature. Whereas in this region here, below the eutectic temperature, we're going to see austenite and cementite. And over here, we're actually just going to see austenite itself. And now this over here is also just ferrite, and they shouldn't ask you a question on this, but that section up there is delta ferrite, so it's just... What do you draw it? And yes. So the answer for that one is obviously going to be austenite. So 7... Alright, inclined plane. So, it's raised by 5 to make an angle of 20, so the initial angle must be 15 degrees. And we know that when we're at 15 degrees, it's just on the point of sliding, so that means that mg sine theta, the force pulling it down the ramp, is going to be equal to the frictional force, mu mg cos theta. So we can rearrange that, cross out mg, and we get mu is equal to tan theta. And that's going to be tan of 15 degrees. Chuck that in the calculator, and get 0.27. Alright, so let's move that. Let's delete all that. Mu equals 0.27. So, now we just have to find the force pulling it down when it's at 20 degrees. Because that's going to be equal to the minimum amount of force required to stop the wheelbarrow from sliding. So that force there, let's label that FF. And that's going to be mg sine theta minus mu cos theta. That's sub in there, 10 times 9.8 sine 20 degrees minus 0.27 cos of 20 degrees. That's... It's going to be 8.65 newtons. Now, this is the difficult part with QCAA, with this question, and it's a multiple choice question, so it's really surprising that they're having trouble here. But what they've said is the minimum amount of additional force required to stop the wheelbarrow from sliding. And we see 8 newtons there, but we also know that if we have 8 newtons, we know that the force pulling down here is 8.65 newtons, so if we oppose it with 8 newtons, we're still going to have 0.65 coming in this direction, so it's not going to stop it from sliding. Which means that it's going to have to be the next lowest option, which is answer C. However, QCAA has put answer D. So they really just need to be careful with their wording here. And, you know, in an exam, they're usually very generous when they give out the marks. But the marking scheme itself, when you look at past papers, it's not done very well, and it can make you panic a lot. But they should be very generous with your marks. They use a lot of statistics and probability to actually mark your exam, and it's marked by like at least 20 different people, I'm pretty sure. So yeah, answer should be C, but they've given D. And so this is just knowing your steels. So high carbon steel, that is going to be used for punching tools. So we know engine crankshafts, that is an automotive component. And if you remember, our automotive components are going to be made of medium carbon steel. And that's 0.3 to 0.6% carbon. Railway tracks they're a special one. So this is another thing you're going to have to learn that I haven't said before when I've gone over metals. I forgot about it. That is made out of a specific section of medium carbon steel, which is just 0.4 to 0.6% carbon. They just need to be that extra bit stiff. And boiler plates, that's mild carbon steel, and that is 0.15 to 0.3% carbon. Punching tools is high carbon steel. If you are working with non-industrial, highly tempered punching tools, though, that would be ultra high carbon steel. Alright. So this is just a SUVET question. So let's use this formula. Although we don't know T. Let me go find another formula without T. Oh, here we go. Oop. V squared equals U squared plus 2AS. So let's just rearrange for acceleration. V squared minus U squared over 2S. And the final velocity is 2.5 squared. The initial velocity is 0, divided by 2 times displacement, which is 0.015, not 15. So, chucking that into my calculator, I get 208.3 meters, 33 meters per second squared. And that is answer B. Last question for the multiple choice. This is a motion question. We haven't seen these in the 21 and 20 exams. I believe it is in the 2024 exam, though, as well, if I remember right. So our different types of motion, we're going to have, first, the easiest one, linear. That's moving in a straight direction in one direction. If we're having rotary, that's going to be circular motion, so moving around in a circle. Nothing more, nothing less, really. And oscillating. This is your pendulum. So if you have an object, whoop, you've got like a yo-yo or something. The motion that it exhibits going back and forward, harmonic motion, that's oscillating. If you know physics, if you do physics, you'll know that that's harmonic motion. And the last one, reciprocal, is a really interesting one. Makes a lot of things possible. And that is the movement back and forwards in a straight line. So just that is also has harmonic motion because it's got that sine wave over time. So you've got to be careful with these because sometimes you'll see that it's actually 2 types of movement. It can't be in this one because they only give us 1. But the answer here is just the piston rod, which is unmoving. It's not that part. So it's going to experience reciprocal force because it's going to be going up to compress the gas, and then it's going to be down as the gas gets sparked and expands. So, start with the question response. Now you do have, instead of 6 short response calculation questions this time, you've got 5, but the marks have stayed exactly the same since 2022, since 2021. This wants us to draw a pulley system to explain concepts of mechanical advantage and velocity ratio. So let's just do this with a simple pulley system, as it asks. Let's draw 2 lines. And let's just say that then we're going to have force of the effort here and force of the load here. And that's a fixed point. It's a fixed point there. So, we have 2 lines here, which means that let's do velocity ratio first. If we want to move this object, this load here, up, let's say 2 meters, then we're going to be subtracting only 1 meter. So say we're going to be moving this load up 2 meters. And because we've got 2 ropes here, to move that distance, we need to subtract 2 meters from the length of each of these ropes, which means this inactive rope, these are the active ropes, this inactive rope here is going to be coming out at a rate of 4 meters for every 2 meters you pull, which means that the velocity ratio of the system is going to be 2. But also the mechanical advantage, we're distributing the load amongst 2 different ropes. And that's also going to give us a mechanical advantage of 2. We could also, because it's an explanation question, they might give you points for just stating this as well. So yeah. let's have a look at how well we did. So we've indicated the number of ropes, and supporting the load proportionately reduces the effort required to move the load. So yeah, we've explained that. It explains velocity ratio, indicates distance moved by the effort by dividing by the distance the load is moved. So I've explained that, I believe. Provides an annotated sketch including effort and load and the distance moved by effort and load. Alright, so that was the 5-mark question. Alright, so this is asking us for industrial applications of steel with a 0.15 to 0.3 carbon content. Now we should know that because low is 0.07 to 0.15, next one up, that's going to be mild. So we're looking for the applications of mild steel. And let's put that in. We've got boilerplates, structural sections, stamps, and forgings. So what have they said? They've said exactly that. So there we go. Easy 4 marks. If you know this, if you know your steels, it's easy marks. Alright, describe the function of a NAND gate. So they might give us a point here for drawing the NAND gate itself and annotating it. We're just saying it's a NAND gate. Describe the function, we'll do that afterwards. Let's label this A, B, and C. Because the NAND gate, it's just going to be the result for AND inversed. So AND is going to be 0, 0, 0, 1, which means that NAND is going to be 1, 1, 1, 0. And our explanation is just that inverse of AND, or whenever it's not both. So all of the marks here are for output is 0 when all outputs are 1. Output is 1 when all inputs are not 1. So that's another mark there. Provides a truth table with 3 correct columns. Oh no, that's for the description. So yeah, we got those marks, just explaining the NAND gate very simply. And the truth table is correct columns. Which is funny, you just basically get 2 free marks for writing out the setup. You can easily get 2 out of 5 marks without even thinking on this question. And the third one is just for C. So, thermal equilibrium. Solidus line. So solidus line, that is going to be from A to E, E to D, and D to C. You could say E to B, B to D, and C. So they will probably either accept EE, B, D, C, or AE, B, D, C, or AE, D, C. Because on their answer they do put AE, D, C if I remember right. The liquidus line. That is the point that separates the liquid from the 2-phase regions. This is a 2-phase region here, and that's another one there. So the liquidus line is going to be A to B, B to C. So A, B, C. Eutectic points. So the way I like to remember this is we've got ick, oid, ick. Ick, oid, ick. Very simple, very easy to remember. That's paratectic then. That's eutectoid. I can't spell, and that's eutectic over here. So eutectic point is going to be, it's going to be B. And eutectic temperature, they're probably going to want us to say that this whole line is the eutectic temperature here. Or do they give, it might be a numerical value actually. So let's guesstimate here. If it's about there, 175, it's probably about 180. And we'll put in the line itself there, just to be sure. The maximum solubility of lead in tin. So that is a line. Oop. So over here, we're going to have, in this region here, we're going to have tin dissolved in lead, because lead has the higher concentration, which means it's the solvent. And over here, we're going to have the reverse, lead in tin. So we're looking for maximum solubility of lead in tin. That is going to be this line here, CDG. Oh no, it's not, because maximum. If they just said solubility of lead in tin, you'd put CDG. But because they've said maximum, that's going to be the point where there's the most lead. So that's just going to be a singular point, D. And the reverse, so E over here. And Alright, so they did say AEDC. They said ABC, B. They said 183 degrees, but it's pretty much if you state any value in the reasonably between 175 and 200, they'll accept that. So they did not give us a mark for that. It's for 180 degrees. And the 2 points D and E. Alright, so in this question we're contrasting mild and high carbon steel. Mild and high carbon steel for automotive subframes. And looking at loads, repeated loads, and high impacts. So we're going to want some perlite for that. But also, we're not going to want a eutectoid composition, because if we have a eutectoid composition, we're going to be seeing a strong material. And we don't want that for subframes. For a car subframe, let's draw it out. Car subframe is the frame that contains the passengers, and we do want this to be rigid. Ooh. We do want this to be rigid, but we also want it to absorb energy, because if it's brittle or even strong, it's not going to absorb the energy as much on the initial impact, and it's just going to transfer all that energy into the passengers, and we don't want that one. We don't want that, because crashes are going to induce a lot of Gs. And if we had these made out of a strong or brittle material, moving it on the highway 100 plus kilometers an hour, that's going to instantly kill the passenger inside. So that's why we generally make subframes out of a stronger material than the body parts, which are these parts on the outside, but also not strong and brittle. So if you remember, the outside is going to be made out of a low carbon steel, whereas the subframe, we're just going to go one up that and do mild. Because you can also relate this with the fact that mild steel is used for structural sections for the same reasoning. We're able to distribute high impacts over time by deforming a little bit and absorbing more of that impact, which reduces the final transfer of energy to anything it's containing. So the relevant mechanical properties that we're going to look at for this is definitely toughness, the ability to absorb energy, and then ductility, because we want it to deform a little bit so it can not have, so it doesn't shatter on high impacts. Sorry, but we also want ductility because we need it to deform. Oh. And the third one that we can look at is probably the yield strength, because we want these materials to have a decent amount of plasticity. Elasticity. We don't want them to immediately crumple, and we want them to be able to bounce back somewhat. And elasticity also relates with toughness, because the higher the elasticity, the higher the toughness, and generally the higher the toughness, the higher the ductility. So these are all interconnected. A lot of things are in the stress for strain diagram. So you contrast these three relevant mechanical properties. So while let's draw something for high carbon steel, so strong material. We have an okay amount of toughness, but if we go and draw a mild carbon steel, we're gonna see it's gonna be less stiff, but it's also going to have a much greater area under the curve. That means it's gonna be able to absorb a lot more energy before transferring that to the passenger, which means we can survive we can survive those high-speed crashes. And we can also see that high carbon steel has a lesser ductility, the length, the amount of elongation that it can undergo before it fractures. We don't want it to fracture, because if it fractures, we're going to get metal shards, and those metal shards could, that could end up in the passenger's neck, and we don't want that. And the yield strength, that's going to control elasticity, and the yield strength is going to be less for mild steel than high carbon steel, but we don't necessarily. But elasticity itself is a combination of yield strength and stiffness, so we're actually going to see a pretty similarly sized elastic region, even though the yield strength is lower. Now we just have to do the microstructure. So if we compare the microstructures of mild carbon steel and high carbon steel, let's make that a bit more of a circle. Let's assume that the high carbon steel is a perfect eutectoid mixture. So we're going to have all perlite regions, and the lamellar lines are going to be going in different directions. that's the reason those grains form, remember? That's going to be an intimate lamellar mixture of ferrite and cementite, where it's going to be one phase though, so it's just perlite really. And that's going to give us a very strong material. So the brittle stiff material combined with the soft, very ductile ferrite it's going to give us a decently stiff, but also malleable stress versus strain graph. Whereas if we have mild carbon steel, we're going to see large grains of ferrite, and in the middle we're going to see, in the large grain boundaries, we're going to see perlite, as we have minimal amounts of cementite. So that large amount of ferrite is going to make it very soft, but the perlite is going to strengthen it. And then the marks there, they go for indicating that ferrite has there's a larger composition of ferrite in mild steel, and there's less perlite in here than higher carbon steel. We've also identified that high carbon steel has a high yield strength, and high carbon steel is less ductile, and mild carbon steel has more toughness. And the last one is that stating mild carbon steel is better for subframes because of its higher toughness and ability to resist or absorb repeated loads and impacts. Okay, so this is probably the worst logic circuit question QCAA has done. So generally you'll put like a sensor here, right? But for this one you're going to need to actually draw a box, label it with a sensor, and write a condition in it, potentially. So let's do it. When staff access the room using a swipe card, so we've got swipe card, let's label it S, and the temperature T, the fans turn on, so F. 1 hour timer, so okay, let's do TI for that. Fans, movement sensor. So our input is going to be the swipe card, S, temperature, the timer, and the movement sensor. And we all want that to match up at fans. So if they access the room using a swipe card, we're going to assume it's activated when it's 1, and the temperature is above 25 degrees. Let's do that. That's the condition I was talking about. They haven't done that before. And so let's draw an AND gate. So let's draw that. So when we've got both of these, we turn on. The fans then turn off after 1 hour of operation. So if... Okay, so we want an AND gate here. If timer is on and still running, but if it's off, we don't want it to activate, so that'll work. The annoying thing is the movement sensor, which resets the timer. I don't understand how you're supposed to reset the timer. How do we do this? If movement sensor is on... So this is very complicated, and I've looked at the sample response for this, because it doesn't really work how you think it would. Logic circuits can be a pain. So what they do is they've got a line here, it goes into an XOR gate, and that goes into the AND gate. And then we've got a branch from the timer with a NOT gate, leading to an AND gate with the movement sensor, which feeds into the XOR gate as well. So what's happening here is that, let's assume this part here, that's on for this situation. So what it's saying is if the timer is on, then and the movement sensor is on, then the reset switcher is off. But this reset switch is only going to activate when the timer is off because of this NOT gate here, and the movement sensor is activated, which is then going to cause a conflict in only one scenario when the timer is on, but that isn't possible to exist, because if the timer is on, that means that this isn't activated in the first place. So that's how that works. It's simpler than I thought. I just couldn't get my head around it the first time. And what else do they ask? Clearly identify all inputs and outputs. We've done that. I believe that's it. So the points here. Clearly identified swipe card input. I think, okay, so what they've done is they've said yes equals 1, but I feel like you should assume these values here, because that's very self-explanatory. That. So I'm going to give myself the marks for this one, but in your exam you should definitely give those conditions under there. If they don't give them to you already, make sure you put those conditions in. And like a condition requirement, that mark for putting greater than 25 degrees. Clearly identified 1 hour timer input. Clearly identified movement sensor input. Clearly identified fan operation output. There's a mark there for having the swipe card and temp sensor link in an AND gate. Condition 1 and condition 2. And 2? What? I don't know what that means, but the diagram looks the same to mine, so I'm going to give myself the rest of those marks. Okay, the next question. Nylon. So if we remember nylon, this is for wear pads because it's got really great thermal and chemical resistance, and it's very tough. We're going to be using that for, gears, wear pads, brakes, etc. We're comparing different types of nylon here. So we're trying to make gears. Now we want gears to be tough because we want them... If we want high torque... No. Wait. So we're looking at gears here. And if you think about gears, typically we want them to have high torque to be able to transmit... to be able to function correctly as speed and torque modification tools. And so for the instance that they're going to be in high torque, we want them to have the ability to do that. And that just means that there's going to be a lot of pressure exhibited on the gear itself. And if there's a lot of that, we want it to be very stiff. Something like that. And we also just have stress here as well. So we want it to be able to withstand a lot of stress inside the elastic zone. So the best candidate for nylon gears is going to be this 0% ENR, and we're going to see that as we increase the amount of ENR, we're going to get a lower and lower yield point and lower and lower ultimate tensile strength, which means that so this is a more ENR decreases the effectiveness of the nylon. Whoa. Let's make this simpler. More ENR is less less effectiveness for gears. So now we just have to include 4 relevant mechanical properties. And there's only 2 mechanical... Okay. And what we've already referenced, yield strength, elasticity, stress, ultimate tensile strength. We've said that it needs to be stiff. Okay. So we need to also reference 4 relevant mechanical properties. So that's mechanical properties. So we're going to be looking at... we've already said it's very stiff. And we know that's the candidate there. That is very clearly a strong material because it's very stiff, but it also has that elastic region there. So we're looking for a strong material. And it needs to be reasonably tough. But if we wanted maximum toughness, we would go with the 20% ENR. Potentially. But we're looking for a combination of the best of these properties, so it is still 0% ENR that is the best candidate there. And we've also said that it reduces the yield stress, and ultimate tensile strength are going to reduce. And the toughness overall decreases. So there we go, we've got 4 properties there And we've got the marks there are for identifying that we're reducing, as we're increasing ENR, we're reducing stiffness, we're reducing tensile strength, and we're also reducing toughness. We've said that. explains appropriately using wording that indicates the inclusion of ENR at lower percentages increases nylon's plasticity. I mean, I don't think necessarily plasticity, but that's very specific. But just mentioning that the toughness overall. It doesn't necessarily also increase its plasticity, so I'm not sure that's a valid answer. Explains that ENR reduces nylon's effectiveness as a material for gear manufacture. So we've done that as well. Alright, question 18. Okay, we need a free body diagram, so let's draw a rocket. So, force of the acceleration, you're going to have force of mg, mass is 2,000 kilograms, from rest to 20 kilometers, so say displacement is 20,000 and 20 seconds. Okay, so we assume rocket's mass stays constant. I have come across a question where they have not mentioned whether this is true or not, and actually assumed that the rocket's mass will decrease as fuel is expelled, but I believe that was a multiple choice question, and in my opinion that was really tricky, and very... in my opinion, that was a very deceptive question. Alright, so let's do this equation, because we won't have to worry. Alright, so we have displacement and we have time. And we know that the initial velocity is 0, so we should be thinking your standard half at squared, and then we just rearrange for a, so 2s on t squared. And it's going to give us 40,000 over 20 squared. Chuck that in. That's 100 meters per second squared. And there's force. And so we're going to take that, and force is equal to mass times acceleration, so 2,000 times 100, and what's that, 200,000 newtons. So that's going to give us 200 kilonewtons, but that's not our answer, and that's because, so what we've calculated here, this value here is actually F net, but that's not the launch force. Because if we have a look at the launch force is going to be this segment of this part here, and then we're going to have the weight of the rocket that we also have to overcome first. So the launch force will have to be F net plus the weight of the rocket, so mg, and that's what, 200,000 plus 2,000 times 9.8, and that's going to give us 219.6 kilonewtons, which is 220 kilonewtons. And the marks is free body diagram with the launch force, or up here, and the weight of the rocket down there. And then we have to determine the weight of the rocket, which we've done here. Essentially, we didn't really have to do that. Find a numerical value for it, you shouldn't, but putting it in that formula should give you the mark. Provides correct formula and substitute values for acceleration, so there. Correctly determines acceleration, 100 meters per second squared. and correctly determines 220 kilonewtons of launch force. So yeah, you've got to be careful there and really know which force they're asking for, and make sure that if they're either asking for a component force or a net force. Okay, what's this? We have an incline of 25 degrees. And we have tension force here. Constant velocity. So there's a constant velocity when it's being lowered, which means that if we say this is FF, FF is going to be mg sine theta minus mu cos theta. Means that in this initial scenario, when we have the before the cable snaps, FF is going to be equal to F of t. So what we're looking for first of all is we need to find the acceleration when the cable snaps, and that acceleration is just going to be FF. So 1500 times 9.8 sine of 25 degrees minus mu cos. What's the friction here? So the initial friction of the track is 0.01. So this is going to be almost negligible. So that gives us 6079.26 newtons. And then we're going to divide that by the mass, which is 1500 kilograms, to give us our acceleration. And that's 4.05 meters per second squared. The next part of the question is, when the velocity reaches 5 meters per second, the coefficient of friction is going to increase, which will eventually bring it to a complete stop. So, we need to find the distance it travels in between the point, this is going to be the point here where the cable snaps, and we need to find then the distance that it takes for the braking system to activate. Which is going to be, let's label that B, and cable C, and the complete stop is going to be S. So to find B, we know acceleration, and we know that the initial velocity is 2, and the final velocity is 5, so what we're really looking for is the formula V squared equals U squared plus 2AS. And so we're going to rearrange for displacement. So final velocity 5 squared minus initial velocity of 2 squared over 2 times the acceleration 4.05, and that is 2.59 meters. And the last part of this question, we're increasing, the second last part of this question, we're increasing the coefficient of friction now. So, at point B, the FF is going to change, and now it's going to be, let's just write the formula first. It's going to be 1500 times 9.8 sine 25 degrees minus 0.6 cos of 25 degrees, and that's pretty substantial. So we're likely going to get a negative value here, because we want it to be, hopefully should be getting a negative value, because we need this to be decelerating. And we do, and it is negative 1781.15 newtons. Convert that into acceleration by dividing it by the mass, and we get an acceleration of negative 1.19 meters per second squared. So we're going to reuse that same formula from before. V squared equals U squared plus 2AS. We know the initial velocity for this section is actually going to be 5, and the final velocity is going to be 0, and we're rearranging for S again. So let's actually just write this out, because we know this formula from beforehand. So V squared, final velocity, 0 squared, minus initial velocity, 5 squared, divided by 2 times negative 1.19. And that is Ooh, that's 10.5 meters. So, therefore, total distance traveled is 10.5 plus 2.59, or 13.09, which is greater than 10 meters. Oh, there's another part to this question, that's my bad. Determine the stop position of the car relative to the warning siren's activation point. Ah. Well, that's just 13.09 minus 10, so 3.09 meters. So they got this, so it's 3 marks there. Correctly determines the acceleration, they got 4.1, so they've rounded here. Yeah, okay, I was right, my bad, I didn't see there was another half to the sample response. So yeah, they had 2.56, but that's their rounding error, because, you know, amazing. And they've got this force, almost exactly. Almost. They got negative 1.19. Correct displacement, we did get 10.5, but they got roughly... it did ask to answer to the nearest whole unit in meters. They'll probably still give you the mark, but I gotta fix that, man. 3 meters. So, okay, so in this question, while we do have 2 active wires, we have to look a bit more closely with this system here. Because, yes, these are the... well, let's first define active and inactive wires. So active wires are the ones that support the load. And they do this when they're connected to pulleys and the load, or another load connecting pulley, but on both sides. So this wire here, because it's free on one end and we're pulling it, that is an inactive wire. And generally, for most simple pulley systems, what we can actually do is just count the number of active wires, and that's going to give us the velocity ratio, but not in this case. And the reason for that is, if we want to, well, first of all, let's say we want to move this generator up 1 meter. To do that, we're going to need to shorten both of these active wires by 1 meter each, meaning we're going to have an excess of 2 meters coming out on this side. So that's 1 meter is going to come out from here, 1 meter is going to come out from here, because we're going to shorten that. So the pulley is where those lines are. But because we're also moving that pulley, this is not a fixed pulley there, we're going to get another meter coming out at the effort point. So we're actually going to get 3 meters. And because velocity ratio is distance of the effort divided by distance of the load, it's then going to be 3. So that's the reasoning for that. Now let's get on with the question. So, the force that we need, the force of the load, that's just going to be our mg sine theta plus mu mg cos theta, and that's where it's the plus because we need to overcome the friction as well as the gravity. And that's going to be 300 times 9.8 times sine of 15 degrees plus 0.3 cos 15 degrees. And that's going to be 1,612.87 newtons. And then to find the force of the effort, because we're assuming the pulley system is 100% efficient because it hasn't said otherwise. Oh no, it has said it's 80% efficient. So actually, before we do that, we need to figure out the mechanical advantage, and that's efficiency times velocity ratio. So 0.8 times 3, that's going to give us 2.4. So what we're going to do next is see that force of the effort is going to equal force of the load divided by the mechanical advantage, which is 1612.87 divided by 2.4. And that's 672 newtons. Did it say answer to 2 decimal places? Of course. The one time I round, it wants me to do it to 2 decimal places. Okay, let me grab up the marking scheme. Alright, so the marks here go to determining mechanical advantage, which is 2.4, determining mass times gravity. Why? I don't need to do that. I like to use this formula, so they'll give me the mark there anyway. Determines force of friction, which I've done. Determines the force parallel, which is that one. No, they're asking for the... They're asking for that. So, correctly, that's perpendicular. Oh, it's not. I was looking at the wrong thing. Still confused what that is, though. Determines the total force, which they did get that. And, yep, the last mark is for the correct answer, which we did get. Okay, so we're looking at 65% lead. So this one is a bit, there's a trick here, 65% lead. If you are confused about which side is which, and what means what for the sides, I tend to not look at these themselves, I tend to look at the axis, because that is undeniable. And actually sometimes you'll see they get these around the wrong way. I've seen them around the wrong way before. It's kind of ridiculous how much is wrong sometimes in engineering. But this will always be right. So, 65% lead, that is going to be 35% tin. So let's draw a line up there. And at 250 degrees, so let's draw that one across there. And let's mark our points. So we have CO, we have Cl, the point in contact with liquid, and we have C alpha, the point in contact with solid. So, percentage of the liquid components for an alloy. So it's not asking for composition, but we're going to do that anyway because it's very, very easy. It is just stating the points here. The C composition of alpha, it's just C alpha, and that's the point there, which we're going to estimate at 15% tin. So let's say C alpha is 15% SN. And CL is going to be 50% tin. And asking for the percentage of the liquid components, so you can either use your lever rule or remember the formula, which is just saying that we're taking the opposite side. So if we want the percentage of the liquid, and the liquid phase is on the right side, so that means we're going to take this left portion and divide it by the entire portion, if that makes sense. It can also, if you are having trouble understanding that, try remembering the formula instead, which is just this formula here. C alpha minus CO over C alpha minus CL. And that's going to be 15 minus 35 over 15 minus 50. That's going to give us 20 over 35. Or, what's that? 4 over 7. 57.14%. Weight percent. We want to, yep, so we've annotated the lead tin equilibrium phase as part of the response. That should be all the annotation that's needed. If there's any more annotation needed, I'm going to be angry. So the marks uses the diagram to determine that area representing 65% lead and 35% tin. So I'm assuming that means this point, this line here. So we can put a mark there. Plot the percentage of liquid or solid at 250 degrees. So that's a mark for that line. Correctly determines the percentage proportion of liquid. So they've used 13. Yeah, so they've just used the point 13, so instead they've gotten 63%. If I had a ruler, we could make this much more accurate. But it should be valid. So let's give ourselves a mark there. So they have gone and also said the composition of the liquid components. Okay, so... Alright. So the mistake I've made here is that liquid components, the keyword here is components, and components is going to be SN and tin and lead, not just the weight of the liquid. So what we can do is take the composition of the liquid, roughly 50% tin and 50% lead. So that means that for the percentage of SN liquid, we're going to take the CL in terms of tin, so 0.5, and times that by the weight of the liquid components, or 0.5714. And what's that? That's going to be 28.57. Now these values aren't going to be exactly what the sample response has gotten because they've used different values. Their answer was, for this one, was 30%, so it's roughly the same. And the percent of lead as a liquid is going to be the composition of liquid in terms of lead. For this one, that's also just going to be 50% lead, but in the sample response, they've used 48% tin and 52% lead, so that's going to give you different values. But for this one, it's just going to be the same thing again. It's going to be 28.57%. So let's do that. If we've got weight of the solid is going to be 3/7, or 42.8%, 86%. The percentage of tin as a solid is going to be, again, a composition of alpha in terms of tin, so this time it's going to be different. It's going to be 0.15 times 0.4286, which is going to be 6.43%. And the percentage of lead as a solid is going to be the composition of alpha in terms of lead, so 0.85, times the weight of the solid, 0.4286. If we do that, that gives us 36.43%. If we add all those values up, so 28.57 times 2 plus those other ones, we should get 100%. And we get exactly 100%. So that's good. All these values should add up to 100%. This is the last question, question 22. Ooh. Alright, so we have 3 different sections. We've got section 1. This is angled at 45 degrees. That is sharp. And it's 25 meters long. And after it reaches this point here, we travel over a 45 meter motorized horizontal conveyor. So this one isn't motorized, this is just a slide. But this is, so we're going to have to worry about having friction. That's section 2. And for section 3, it's 30 meters long. And it has variable speed, so I'm guessing that's going to be important later. I'm going to assume that section 2 has the same diameters as section 3 conveyor. So let's say that in the assumptions. Determine the revolutions per minute if the kinetic coefficient between luggage and steel. Okay, so we need to satisfy both of these criteria when mu is 0.42. That's for section 1. So the coefficient of friction for the horizontal conveyors, there isn't one, by the looks of it. They've only stated one for luggage and steel, and the only steel thing we have is the ramp. So we're going to assume it's going to be 0. So first thing to do is figure out how long it takes to get down section 1, because that's not going to change. Section 1. So the force we're going to experience is just going to be standard FF, mg sine theta. This is really, really powerful formula right here for the engineering external. And so we don't know how, we do not know the mass, but actually we don't need to know the mass because we're just looking for acceleration. So let's change that and remove that. And sub in, sine 45 is root 212 minus 0.42 times root 212. That gives us 4.02 meters per second squared. So, condense that a little bit. Alright, I give up. What do we have to do next? So it's 25 meters long, so we're going to need displacement. Alright, so we're assuming initial velocity is 0. And we don't know final velocity, and we don't know time, so the formula we're going to use is v squared equals u squared plus 2as. We'll rearrange for displacement, and we're going to get... No, not displacement. Oh, we already have final velocity. We want final velocity. So that's going to be u squared plus 2as. And... Yep. So that is 0 plus 2 times the acceleration, 4.02, times 25 meters. Root 201. 14.18 meters per second. Now, the big question here is, we would just be taking the horizontal component of that, wouldn't we? Because the vertical component's going to get absorbed by the ramp. So now for section 2, we're going to have to let's go ahead and remove that, because we don't need that anymore. In fact, just let me delete it. How do I... Alright, there you go. Acceleration is 4.02. So now that we know that the velocity coming off this ramp is 14.78 meters per second, the horizontal component of that is just root 212 times 14.78, which is 10.02 meters per second. Or... No, because we don't actually... Just realized that we don't actually need this. We just need time. I'm a doofus. Alright. So, that's so much for nothing. So the formula we're actually going to use is half at squared, and then we're going to rearrange for t, which is 2s on a square root, which is 2 times 25 over acceleration 4.02, 3.53 seconds. That's for section 1. Alright. So if we want... Whew. So let's label time for section 2 T2 and time for section 3 T3. Now we want T2 to be half of T3, because we're going to spend half as long in section 2 as we're going to spend in section 3. So now that we know that, we also know that T2 plus T3 plus 3.53 is going to equal 20. So let's rearrange for T3. We're going to get 16.5747 minus T2. And we sub that back in there, we're going to get T2, 2T2 is going to equal 16.47 minus T2. So we're going to get T2 is 16.47 divided by 3, which is 5.49 seconds. So, now that we know that, let's take that and put it up here. We also know that T2 is half of T3. Oh. So we also know that T3 is going to be double that, which is 10.98 seconds. And we don't really have to do anything for section 2 anymore, it's all about section 3 now. So let's see, we want to find revolutions per minute. If we want to take 10.98 seconds to cover this distance, means that the speed at which we are going is going to be 30 divided by 10.98, which is 2.73 meters per second. So that means that every second we want 2.73 meters. We want one of these rollers to rotate 2.73 meters worth of material. And so the first thing that we're going to need to do for that is figure out the circumference, which is just pi times diameter, or pi times 0.25. And that is 0.785 meters. And if we want 2.73 meters, we are going to have to do 2.73 divided by 0.785, or 3.48 revolutions per second, not per minute. Revolutions per minute is going to be 60 times that, which is 208.66 RPM. Let's check that. Forgot to round again. I'm always forgetting that. 209 RPM. Otherwise, that is the correct answer. Let's check the marks. So, we've correctly identified that there was two forces acting on the ramp, the friction force and the gravity force pulling it down the ramp. We determined the net force. We determined the acceleration, 4.02. We did provide many assumptions in explanation of doing the question, although I didn't write them down. Make sure to write those down. Provides correct formula and substituted value for displacement. We did that. Correctly determines the time for section 1, which was 3.53 seconds. Time required. There's no mark for time 2, but there is the mark for 10.98, section 3. Correct. Also need to find the velocity. We did that beforehand. 2.73 for section 3. And correctly determines the answer to the nearest whole unit with correct unit provided. So, I didn't do that. That should be generous. Usually they're generous though, so I'm going to say I got that one. And that's the exam done. So, yeah, I know one thing I need to work on, if I was doing this again, is really remembering that last whole unit. Because it seems to be every third question I am losing marks for it. And also just reading the question in general. So, yeah.